last time we talked about rivers and streams and water, groundwater, that kind of stuff. Today we move on to the next water-based subject, which is ice and glaciers in particular. So, ice is extraordinarily important for our planet for a few reasons. Number one, that's where the majority of the fresh water is locked up. Number two, ice on the planet controls sea level more than anything else. And sea level goes up and down, mostly due to changes in climate and how much ice is locked up. If you melt all the ice on the planet, how much does sea level come up?
A lot.
700 meters.
About 300 some odd feet.
Wow.
And that's sea level. Not, that doesn't mean feet from
That's
the
a
beach,
lot.
but so in places like Virginia, for example, that brings sea level up to Richmond,
Wow.
up to Columbia, South Carolina.
Dang.
Well, it gets rid of pretty much the entire state of Florida, that kind of stuff.
Good.
Conversely,
We don't need them.
if you lock up a bunch of water in ice, you can drop sea level all the way out to the edge of the continental shelf. So minor changes in ice on the planet results in major changes on where the beach happens to be located. And the third thing is weather. We have been in this pretty stable climate now for about 4,000 years that is driven by heat along the equator. We'll talk a lot more about this as we go on the next couple weeks. But heat on the equator and ice caps on either pole. And those two things in particular have resulted in the climate that we're all used to. With, moderate climate here in Virginia and storms coming and going, you get seasons and that sort of thing. Colder north, warmer south. If you get rid of the ice on the ice caps, if you get rid of the ice along, up in the North Pole area, sea level, not sea level, but the sea ice up there, that refrigeration disappears. The sea ice up in the North Pole keeps things pretty cold. And that difference between cold in the north and hot along the equator drives weather systems where we live. But if you get rid of one of those two things, if you get rid of that refrigeration in the North Pole, then the jet stream that drives the storms changes. And we'll kind of come back to that a little bit later. But for now, yeah.
So would everything be the same, like weather all over the place?
Well, if you talk about things like climate change and the possibility of the sea ice disappearing on the North Pole and the ocean warming up as a result, yeah, there's a lot of research going on right now into the sea ice is disappearing and the ocean water temperatures there it's warming. So if you take that to fruition, then what happens to the jet stream? Because you have this refrigeration up here and the heat on the equator, the jet stream is driven in between the two. So if you would get rid of one, what happens?
Yeah.
Nobody really knows the answer to that.
So if all the glaciers melted, it wouldn't ever snow here?
It snows here now.
Yeah, barely.
Got it.
What is?
I will say that the old timers in Rockbridge County talk about the days when they had ice harvesting businesses for the lakes around here. Before refrigerators, you were able to plug in and get it cold. When you had to have ice boxes, they used to harvest ice on the lakes around here to supply ice for the refrigeration. That hasn't happened.
20, 30 years.
And the old timers themselves say that was something that disappeared, it's been a long time, at least the 70s. Since there's been ice to that degree on the bodies of water.
Well, we used to get like feet of snow here, at a time.
Where was the picture at? Was that in Norway? The first
previous one?
Yeah. Was that in Norway? You take it?
Yeah, I did. And in fact, this picture I took in 1994, and the ice was right down here. That's my wife. But today, the ice is over the lip. You can't see it anymore.
Really?
Yeah, it's retreated up there quite a bit.
Oh, have you seen those videos where like the glaciers fall apart in like the lake and then they create the big old waves?
Yeah, that's dangerous.
That's really good.
So let's talk about glaciers, talk about ice and what that happens to be. So a glacier forms when it snows, and it snows a lot, and it doesn't melt. And when you do that, the snow itself goes through a process where it turns into a nice pretty snowflake, the kind of thing that if it's really cold, you know, you kind of blow it off the deck with a snow blower or something like that. As that accumulates though, it changes and goes through a process by which it goes from a snowflake to granular snow to what's called firm to glacier ice. Basically what happens is the snow accumulates, it heats up a little bit, and it gets pressed against each other, the snowflakes do, and there's a lot of pressure involved, and they slightly melt a little bit. And that turns it into you know, a hard, dense chunk of ice versus what may be accumulated in your front yard during a snowfall, which is nice, you know, playful snow. And you see this a little bit around here when maybe it does snow enough and you know, they plow the driveways and they plow the parking lots and that sort of thing. And even just a day or two later, that snow has kind of compacted a bit and turned itself into something relatively hard. And if we lived in a part of the world where that snow pile might persist on the edge of the parking lot for a few months, then it really does turn into this hard, sort of granular, ferny type snow.
What's the difference between glacier ice and just regular ice?
Glacier ice is going to be really hard and dense. So, for the most part, you're talking about areas where it snows year-round. So, up in alpine areas, for example, maybe it doesn't snow year-round, but very close to snows year-round. In the summertime, some of the snowpack melts off, but the glaciers form in areas where the snow doesn't melt, and it accumulates and accumulates and accumulates, and it can be very thick. In Antarctica, those glaciers can be miles thick. In a picture like this, you're talking maybe a few hundred feet thick, something like that. Alpine glaciers form in alpine regions. So in areas where you get above the snow line, it snows year-round for the most part, and you're not melting it all off during the summertime. If you're not melting the snow off during the summertime, it accumulates and it gets to a certain thickness and it begins to flow. So glacier ice is really hard and dense, but it's also not entirely solid. Gravity will take over and the ice will flow downhill over time. So in an alpine area, the glaciers are separated by what's called the snow line. And the snow line is, you get above that, and it's going to be snowing year-round by and large. Below the snow line, that's where the snowpack melts off. And the difference is that up here, where it's snowing year-round, the ice gets thick enough that it flows downhill in these valleys. And so below the snow line, the snowpack melts off during the summer, but the glacier ice is thick enough to persist. It flows like a tank tread, and flows over on itself and cracks up into crevasses that we're talking about.
That glacier's still underneath like the snow, like
Yeah,
lines
so
up, right?
the snow line here, the ice is under there.
And how far up does it go? Like does it keep on like replenishing itself like at the top of the
Yep.
mountain, or is it just
It's
like,
replenishing. Especially, you know, when a picture like this is taken, you're talking maybe mid-August to mid-September, something like that, when the snowpack is really melted off. But it's going to be snowing from mid-September to mid-July.
Yeah.
You know, that sort of thing. So, but yeah, it just keeps flowing down. The more snow you have, the bigger the glaciers get. The less snow you have, the smaller the glaciers are. They ebb and they flow. Second major type of glacier is called a continental glacier. This is where the ice has accumulated to the point that it's gotten deep enough to smother the mountains and covers an area the size of a continent. Now, on Earth, back during the last ice age, these were much bigger and covered larger areas of the continents, and we'll talk about those. But now we're left with two areas, Antarctica and Greenland. These numbers here are the thickness of the ice in meters. So they're pretty thick. A mile or so thick. That's a lot of ice. And in places like the South Pole or up here in Greenland, the ice, actually the elevation up here is on the order of, what's the number? 11,000 feet, something like that above sea level. So you're pretty high up And the same is true in the South Pole. There's so much ice, you're pretty high up into the atmosphere. And that stuff flows out in all directions and eventually empties into the sea. But they're very thick and they occupy an area the size of the continent. We'll come back and talk about these. In between the two, you have what are called glacial caps. And glacial caps cover a smaller area. They're not alpine glaciers, but they're not continental glaciers. But they're thick enough to cover a few mountain valleys. And we have these in Alaska, southeast Alaska, for example, places in Norway, a few areas where you can go up and on top of these glacial caps. So let's begin by talking about alpine glaciers and work our way into continental glaciers and go over a little bit of the terminology. Well, with an alpine glacier, you have this game of accumulation versus wastage. Accumulation meaning above the snow line, you're accumulating ice all the time. That ice moves downhill and into the zone of wastage where in the summertime the snowpack melts off and you begin to melt some of it. And the difference between the two depends on what is the climate like? Is it a colder period? Is it a warmer period? And what's the weather like? Are we putting more precipitation on here or are we in a drought? And that causes the glacier to ebb and flow like water in a river. These things move over on themselves like a tank tread, and so it cracks into crevasses. And these crevasses look a bit like this.
Wow.
They're pretty intense. Everest Base Camp people that hike up Mount Everest have to go through one of these fields called Kumbu. It's called Kumbu Ice Field. They have to go through this stuff.
And that's ice?
That's ice. It's all cracked. It's dirty.
Ugh.
Oh, that's I thought.
How deep are those little crevices?
They can be a few feet deep. They can be 1,000 feet deep.
Wow. No kidding.
Glaciers, alpine glaciers, are extremely dangerous to go out on because in the summertime, when the snowpack melts off, you can see these things, and you don't want to go down one of these things because they're V-shaped, so if you fall down, you tend to kind of wedge your way in there. And if it's deep enough, you disappear, you end up coming out 4,000 years later.
Wow.
But in the winter and the spring, and then at that kind of time frame, the snow will fall on here and cover it, and
You won't know.
you don't know if you're crossing one of these things. You don't know if you're on a snow bridge and you fall down. They're extremely dangerous. So if you've watched shows like Survivor Man or stuff like that, you see them going out with these glaciers and they have they're either all roped together or you tow behind yourself a 10-foot wide stick or something
Yeah,
in case
that's
you
right.
fall down.
That's why you always gotta have a.
And they have a
walking
pole
stick.
in front of them to see if they're, about to walk out onto one of these things.
It's like the Transformers, the dude that falls into an ice cave. How do those things form? Like,
Ice
is that
caves?
yeah, like the
Yeah.
same thing.
All right, so
Yeah, Sam's grandpa.
these things move over on top of each other, right? There's a bunch of stuff up here moving, and it's moving at a faster rate than what's going on down here where it's up against bedrock. So it slows down and causes it to fall over on itself. Down here, it's a little warmer too, so it melts.
Oh.
And so you get little rivers and rivulets coming out of the base of the glacier as it melts off down here on the bottom.
Just open up some stuff in there.
Yeah, basically opens up. So that's the ice caves that come out at the bottom, look like that. But just like a river, ice is extremely abrasive. And so as these glaciers move down the valleys, they scour out the land, just like a river does, and incorporate all its sediment into the ice. And for this reason, glacial ice is usually not this sort of pristine, pretty ice cube kind of stuff. It's dirty. It's got a lot of dirt in it. And that dirt organizes itself into what are called moraines. A lateral moraine is on the edge. An end moraine is at the very end. A medial moraine is in the middle. And a medial moraine forms where two glaciers come together. And the two lateral moraines come together to form one medial moraine. A lot of glaciers have numerous moraines in them that indicate how many tributaries are farther upstream. In the summer, when the snowpack melts off, you can see these things, you can walk up them. sort of. In the winter, they're all covered in snow. But because this stuff is moving downhill, and you put a time-lapse camera up there, some of these glaciers are moving in feet per day downhill. It just scours. Ice is even worse than river water in terms of scouring the landscape. This sediment, this glacial sediment collectively is referred to as till, glacial till. It's a hodgepodge mix of unconsolidated sediment that represents all the dirt farther upstream this stuff moved down through. And it's a little bit unique in the world of geology sediments. But alpine glaciers are very effective at changing their environment. So in a mountainous area like this, which would be unglaciated and relatively normal, most of the rivers that form in a place like here, for example, do so in what's called a V-shaped valley, kind of a narrow, steep little valley. The Mar River is a bit like that. But if you put ice in there for any period of time and allow the ice to form, because ice expands 9%, or water expands 9% when it turns into ice, and it pushes its way down, it takes what's called, kind of an unglaciated V-shaped youthful river valley, turns it into a glaciated system, where the V-shaped valleys now become U-shaped, and you have various topographical features that result from the ice carving the landscape. It's very unique to alpine glaciers. During the last ice age here in North America, we are right at the very southern extent of where the Continental Glaciers got to. So you get a little bit farther north from here, the mountain valleys change from something you might see in North Carolina, where if you've ever poked around the Smoky Mountains or places like that, you have very steep, closed, dense mountain valleys. You get farther north and they open up a little bit, up into Vermont and New Hampshire, and Newfoundland and Labrador, because they've been sculpted by glaciers. The valleys are U-shaped. You have mountain cirques up here. If you're a skier, these are called bowls. Ariettes, which are the knife-edged ridges between two valleys. And horns, which represent at least 3 glaciers coming to a point, like the Matterhorn in Switzerland. So if you melt off the glacier, it looks something like this. If you get rid of the glacier, you're left with this topography that's very unique to something where there used to be glaciers. And there might still be farther up. Cirques, horns, tarns, little lakes. So if you go hiking in the Rockies, for example, if you're in Wyoming or Montana or Colorado, someplace like that, you get pretty high up in elevation. That's an area that has experienced glaciation, and so the topography looks like this, as opposed to something like North Carolina, which doesn't.
Wait, for those hanging valleys, does it just like drop off really quick?
Yeah, so hanging valleys represent an area where a tributary glacier was coming down into the main trunk itself. And when the ice melted away, you're left with this, basically this, cliff face right there, and water that comes down forms a nice waterfall. I'll show you a picture of this in a minute. So when you get rid of the ice, the valleys look like this. A nice U-shaped valley. Sometimes you'll still see a glacier in there, sometimes not. So if you've ever spent or had a chance someday to spend time in an area that has been sculpted by glaciers, like Alaska, or Scandinavia, or Labrador, or Patagonia, something like that, southern New Zealand, the landscape is very similar to this, and the valleys are very U-shaped. And to your point, a hanging valley looks like this.
Oh, that's lit.
Where you had a tributary glacier flowing into a main glacier at some point in the past, and then left kind of cliff face and water flows down there. So the Yosemite Falls, for example, in California, is an example of that. Some of the world's biggest waterfalls, not the biggest ones, but some of the world's prettiest big waterfalls are hanging valleys like this. they're hard to get to. Those hanging valleys are hard to get up into, so obviously this is where all the dinosaurs still live in the movies. These hanging valleys that are hard to get up there because they're cliff faces that you have to.
Ewing line.
Huh?
Ewing line.
Yeah.
Stegosaurus.
Yeah. That's where T-Rex still is. Horns like the Matterhorn in Switzerland, typically three-sided. You got one glacier here, one glacier there, and one glacier back over there. So those are alpine glaciers. I'll blow through those pretty quickly because they're pretty simple. Continental glaciers, though, are completely different. Continental glaciers have areas along their edges where you might have some alpine glacier features, but the ice sheet itself is much, much larger and extend over something the size of a continent. And that changes the continent, whereas alpine glaciers will affect things locally, you know, cause a valley to be sculpted or make a pretty mountain range. Continental glaciers change everything. On the edge of the continental glaciers, like on the edge of Greenland, you have stuff like this. You've got the ice sheet up here, and ice flowing out of there feeds down through what are called fjords. And you get little glaciers occupy these fjords in through here, and those glaciers are moving all the time, feet per day, and dumping a lot of ice into those fjords. And that ice, especially in the spring and the summer, works its way out of those fjords into in the case of Greenland, the Atlantic Ocean. And those icebergs can be really big. And sometimes they take out boats like the Titanic. So you can go to like Newfoundland, for example, and in the middle of June or July, sit there looking out into the Atlantic Ocean and see these gigantic icebergs just sitting there as they flow south out of Greenland and melt into the Atlantic Ocean.
But is that the one where there's like the big rock that people sit on and look into it? You know what I'm talking about?
No.
The fjord. I'll find it. It's like I feel like it's like I think it's like a glacier.
Yeah, I mean these kinds of fjords, for example, are really common in Greenland, Labrador, Scandinavia, Alaska, where you have larger glaciers dumping ice into the sea. Yeah, and as it does so, it makes those big icebergs that float out and eventually melt. Yeah, some are bigger than others. But even in today's world, crossing the Atlantic Ocean by ship, you have to be aware of icebergs most of the year, especially in the spring and the summertime as those things flow out. Especially if you're in a ship and you're going at night or it's really foggy. And it's still a major hazard to shipping, even in today's world. But one thing that continental glaciers do is they put a lot of weight onto the land. So think about this for a minute. You've got something the size of Antarctica that might be 1 or 2 miles thick, and it's just sitting there on the land. That puts a lot of weight onto the land and it pushes it down. When the ice melts, that land rebounds. That's called crustal rebound. And in areas of North America, for example, during the last ice age, 18,000 years ago, we had 1 or 2 miles of ice over North America, pushing down on the continent. And as that ice melted, it melted really quickly. In a period of maybe 1 or 2,000 years, it almost completely disappeared. And the land has been rising ever since. So from here and points north, the land is slowly rebounding, and it's measurable. It's about this much every year. North America is rising up in response, rebounding, basically. What that does is this to the rivers. Around here, the James River, for example, you are used to going to the river by walking to the edge of the river and walking straight in. No big deal. If you go farther north, if you go into the Dakotas, if you go up into Canada, this is northern Greenland. All the rivers have cut down in response to the rebound. So they are all in short, little, narrow valleys, and it's hard to get to the water, for the most part. So all rivers have downcut because they like to stay at the same elevation as the land rebounds around it. So in places like the Dakotas, you're the riverbanks are like this. It's hard to get down to the water because the water has stayed put, the land is rising around in response. Happens less so down here. These continental glaciers trapped a huge amount of ice in them as they moved. And in response to them moving over the land, they also incorporated a lot of sediment. That glacial till was tremendous. As the glaciers moved over the land, they incorporated a huge amount of till, but they also sculpted the land surface in North America. And again, just north of here, even up into New York State, northern Ohio, places like that. When the ice melted and disappeared, it left behind a topography that we see today and recognize. For one thing, there's what's called a ground moraine. This is the glacial till north of this area. It's random chunks of small rock and big rock. It was brought down from points north as the continental glaciers formed. The main reason why, when you go north here into New England, you go into Pennsylvania, Connecticut, Vermont, New Hampshire, places like that, you will notice that there's a lot of buildings built out of rock. There are lots of rock walls everywhere on the edge of pastures and things like that. That's glacial till. Those are the bigger chunks of rocks that people picked up from the fields and then lined up as walls or used it for building material so they could farm. They had to take all the big chunks of rock out of there to do it. And so you go up into New England, you have rock walls everywhere as a result of the ground moraine and the big chunks of rocks that are in the ground moraine. Smaller hills were sculpted into what are called drumlins. Streamlined things called drumlins, where the steep side is the upstream side. There are tons of lakes. Minnesota is the land of 10,000 lakes or something like that. You get these roundish shaped lakes that dominate the topography in North America. Minnesota, Wisconsin, and up into Canada, up here, that's the dominant topography. There are millions of little teeny round lakes everywhere. You ever decide to go fishing in northern Canada, you fly into these things. There's millions of them everywhere. Those are called kettle lakes. Those are big ice cubes that as the continental glaciers receded and left behind big chunks of ice that melted into the ground, left a hole. There you go.
How deep are those?
Usually not very deep.
Well,
I mean,
how
not
they just
terribly.
how they just make the lake? I'm confused by that. Like, do they just melt it and they loosened up the ground or something?
It just made a depression in the ground. That depression filled with water and stayed put. This is the stuff that ice road truckers drive over all the time. Watch this. That sort of thing. The bedrock itself, if the glaciers moved over something that was more like a mountain or a small mountain, and it was bedrock, not soil, it sculpted it to look like this. The downstream side was an area where the ice moved over and plucked chunks of rock out, which made that side steeper, and the upstream side was smooth. And a lot of the mountains that we have, I should take a little more pictures, but if you go up into Vermont, for example, look at the Appalachian Mountains there, look at the side view of the Appalachian Mountains, you'll notice that a lot of mountains look like this. There's one side is steep, and the other side is more gradual as these continental glaciers move over that area.
Like those glaciers are from obviously how long ago?
Yeah,
Like a while ago though?
yeah,
Because obviously there's nothing there now, but
yeah. Recent, but not that recent. 18,000 years ago is when it ended. The upstream side, as the ice moved over the bedrock, scratched it, and you get what are called glacial striations on the bedrock. They're very common in that area. So the last ice age in North America at least looked like this. So if you go back from about 100,000 years ago to
It would've been
18,000 years
frozen.
ago, it looked like this.
I would be fine.
That was the last ice age. Ice ages happened every so often due to changes in orbit of our planet around the sun. Every now and then we get a little bit farther away from the sun, which causes the planet to cool dramatically, and we have an ice age. And then that ends, we get a little closer, and the ice melts. These happen on cycles about every 800,000 years or so.
Does that have to do with like how the Earth rotates? No.
It just has to do with orbits are not perfectly circular around the sun.
So like
And they
when
wobble.
Iceland like doesn't get any, like it's sunny 24 hours of the day. Is that like the same kind of idea, like because of the sun hitting them all the time? Or is
That's
that-
because our Earth is tilted.
Oh, okay.
So, and the sun's over here. So when your tilt is away from the sun, you're dark. As you come around in the summertime and you're facing the sun, you're
It's light all the time.
it's not all the time.
I watched like some Netflix show. It was like the Ice Age, like in 7,000 BC or something, right?
Yeah.
So was there just like a giant flood or so? It was all every like it was like ancient civilizations.
Did you watch Ice Age?
Let me come back to that. Yeah, I mean, that's not entirely wrong.
There was like a big flood that like destroyed all of them.
I mean, our orbit around the sun is not perfectly circular, and it wobbles a little bit on an 800,000 year period. And when it gets a little farther away, things cool down. When it gets a little closer, it melts. It's has nothing to do with, more recent climate change stuff. It's a kind of a general cycle. But when we go into an ice age, basically what happens is it gets
Ice Age.
real cold, real quick up here. It snows a lot, and you get glaciers that grow. Not just in North America, but in Europe, Asia, and also in the southern hemisphere. But so 18,000 years ago, this is the maximum extent of what this looked like in North America. And this is actually kind of cool if you think about it. So you've got ice that's 1 or 2 or 3 miles thick right here, and it's cold all the time. And then you have the equator down here. And the storm track was pushed real tightly in between these two. And I can only imagine what the storms must have been like back then. I think it'd be pretty cool to witness. Because the storm track in today's world gets pushed between the two as well, except the ice is just right up here. And the equator's down here, so it spreads out. Back then, it would have been pushed right into here. That would have been pretty impressive, I think. We're really close. This is Virginia. We're really close to where the ice sheets stop. So you have to go just a little bit farther north to see it. The ice ebbed and flowed over time. And those were given names, the Wisconsin age, the Illinoisan age, and so forth, as the ice ebbed and flowed and deposited lots of till each time. So this is a maximum extent right here. We're very close, but not quite. You have to get a little bit farther north to see this. So for example, if you've ever driven across Ohio, so if you cross into Ohio, this area here is still relatively hilly. And then you hit central Ohio, and the landscape just goes into here, through Indiana, at least central Indiana, and a lot of Illinois. That is pancake flat. Lots of windmill farms, things like that. The same is true up into Wisconsin, up into Minnesota, and parts of the Dakotas. Because the landscape was just pushed flat, bulldozed.
Why didn't that happen in like other countries or other states in the north?
It did. It
Oh,
did.
okay.
If you go farther, and I'll get to this in a minute, if you go a little farther west, come over here, you got the Rocky Mountains. And the Rocky Mountains
Obviously.
prevented that. But they still had their own issues as far as ice goes, and we'll get to that. And certainly Europe, Asia, Southern Hemisphere, they had it as well. But there was a huge amount of ice and a huge amount of sediment in these things. And when the ice melted, they left behind end moraines. And in this part of the world, this is what these look like. This is the maximum extent of the ice sheets right here. And they left behind a huge amount of sediment as they backed up. It's like a bulldozer, you You bulldoze across the land, you push a bunch of sediment in front of you, and then you back up and you leave a mound behind. These end moraines we call Long Island, Martha's Vineyard, Nantucket, Cape Cod. It's all glacial till, hundreds and hundreds of feet thick, left behind at the edge of that continental sheet. It's been weathered and eroded and vegetation has grown, but those were big end moraines. Some areas are full of drumlin fields, little slough mounds and stuff that were shaped. And if you go into the lake effect area of New York State, around Buffalo, Rochester, below Lake Ontario, the topography through here is dominated by these drumlin fields. Where, if you look at a topographic map, there's just thousands of these things. They're maybe 30, 40, 50 feet tall, something like that. It's streamlined in a very specific shape. Just all over the place. Just debris from these continental glaciers. All right, I'm going to stop it there.